Hi all, I am K. Surya working as Assistant Professor in the Department of ECE at SNS College of Technology. In this video, let us see about Hall effect. Hall effect is a phenomenon observed when a current carrying conductor or a semiconductor is placed in a magnetic field that is perpendicular to the direction of the current. This creates a voltage difference across the conductor perpendicular to both the current and the magnetic field. This voltage difference is known as the Hall voltage. The Hall effect is used to determine the type, density, and mobility of charge carriers in a material. It also serves as the operating principle for all effect sensors, which are widely used in various applications, including position sensing, speed detection, and current measurements. So this Hall effect was discovered by Edwin Hall in uh, 1879, and it provides a valuable insights into the nature of the electrical conduction in materials. When a current flows through a conductor in a magnetic field, the moving charge carriers experience a Lorentz force, which deflects them to one side of the conductor. So this accumulation of charge on one side creates an electric field that opposes the Lorentz force, eventually reaching an equilibrium where the electric and the magnetic forces will balance each other. The resulting potential difference across the conductor is the known as the Hall voltage. So next, let us consider that a rectangular conductor with length L and width W and say thickness is T carries a current I in the X direction. A magnetic field B, when it's applied in the Z direction, which is perpendicular to the current flow, the moving charge carriers, that is either electrons or holes, experience a Lorentz force, which is given by the equation here, which is F is equal to Q into V into B. Where Q is the charge of the carrier, which can be negative for electrons and is positive for holes, and V is the drift velocity of the charge carriers, and B is the magnetic field vector. So next is before going to the advantages, we'll see that the force which is created because of this Lorentz force deflects the charge carriers, causing them to accumulate on one side of the material. So the accumulation of the charge creates an electric field that opposes the magnetic force, eventually leading to a state of equilibrium. The Hall voltage is directly proportional to the current, the magnetic field strength, and inversely proportional to the charge carrier density and the width of the material. Next, we'll see the advantages of Hall effect sensors. So it can detect small changes in magnetic fields, which indicates that it has high sensitivity. Then it can be easily integrated into electronic devices. So its size is very small and relatively inexpensive when it's compared to other types of magnetic field sensors. So its cost is very low and it can withstand harsh environmental conditions. So it is very robust and its lifespan is long and it has a stable performance which has a good reliability. Next is limitations of Hall effect sensors. So this Hall voltage can be affected by temperature changes. So it's very sensitive to temperature. And some of the sensors may have a small offset voltage even in the absence of a magnetic field. Also, the relationship between the magnetic field and the Hall voltage may not be perfectly linear. So it's said to be a non-linear, and mechanical stress can affect the performance of the sensors. So next is the applications of Hall effect sensors. It's used in various applications like material characterization, where it's used to determine the type, density, and mobility of the charge carriers in semiconductors and metals. So this information is crucial for understanding the electrical properties of materials and for designing the electronic devices. Next one is it's used in magnetic field sensing. Hall effect sensors are widely used to measure the magnetic fields. These sensors are small, inexpensive, and they are reliable, making them suitable for a wide range of applications. Next is medical devices, where Hall effect sensors are used in medical devices such as pacemakers and infusion pumps to monitor and control the flow of the fluids. And finally, it is used in navigation systems, where it's used in the compasses and other navigation systems to detect the Earth's magnetic field. So, if you understood the Hall effect sensor and its working in detail, let us take up some assessment questions. So the first one is the Hall effect is mainly used for measuring. The answer is magnetic field. Hall coefficient depends on the type of the charge carriers, whether it can be an electron or a hole. And the Hall voltage is directly proportional to the current magnetic field, and inversely it is proportional to the charge density. Thank you for watching this video.